Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, let's get started. Welcome to our session of sensors across scales. Our first speaker today is Dr. Yong from National Center of Supercomputing Applications at UIUC.
Thank you. Today, I will present our position paper talking about exploration of real-time provenance-aware virtual sensors across scales for studying complex environmental systems. I would like to acknowledge my co-authors, Alejandro Rodrigo, who is currently actually in Amazon, working for Amazon actually. So he just left last month. And Joe Future, who is in the audience, and Rob Cooper, and Jim Myers. Jim also left NSSA. So he's in another school, RPI, Rensselaer Polytechnic Institute. So I would like to start with a broad picture about what people consider complex environmental systems. Actually, more than 7 years ago, NSF released a report called Complex Environmental Systems with the subtitle Synthesis for Earth, Life, and Society in the 21st Century. And there are a few highlights in that report, and I think they are still valid. One of them is the coupled human and natural systems, which basically you need to study the complex web of environmental relationships and feedbacks at the diverse temporal and spatial scales. And then the other highlight they point out is so-called coupled biological and physical systems, which include the systems, processes, and dynamics that shape the physical, chemical, and biological environment at all scales. So basically, complex environment systems they are cross-scale and cross-domain, and by nature is interdisciplinary. And in the meantime, in the past 7 years, there are quite a few reports from the computational science point of view, or from the data-intensive research point of view, or from cyber infrastructure point of view, talking about how those challenges in a broader science domain. I won't repeat all those, but basically the fourth paradigm is one of the latest one, actually was released from, published last year from Microsoft Research. So what we really need to do is that bring that broader computational data-intensive research perspective to solve complex environment system problems. And our motivation is basically by the diverse problems arising in environmental informatics areas. So we have heterogeneous sensor sources. This include mobile participatory sensing, citizen sensing sources, as well as multi-agency sources. And they could be point-based data or radar data or remote sensing data. And there are quite different and evolving needs from various environmental observatories, and at least a few of them which are basically the motivation that we did our provenance-aware virtual sensor work. This includes repurposing and reusing of sensor data and sharing, resolve the resolution gap problem, where you have spatial temporal resolution for your decision support or modeling, but you don't have that ready anywhere. And you also have real-time feedback control-based data and model need. And finally, people talk about data-driven model as well as physics-based model, and how to harmonize those two approaches together. So ultimately, the goal of environmental informatics research is to integrate in data and models of multiple physical processes and human influence at different spatial temporal scales to achieve holistic, predictive understanding of the complex environment systems. And that means the increasing of both the studying the research scope size, the problem size, as well as the scope, where you have multidisciplinary by nature. So I would like to give you an example complex environment system that currently we have work on in Illinois, where I come from. We have an IACAT project, which is an Institute of Advanced Computing and Application and Technology in Illinois, where we have quite a few diverse areas that we want to integrate. On the bottom part, you can see we have a plot scale field where we have mobile modes, those intelligent sensors to measure nitrogen and other things. And we have tire drain and other sensors around that 40-acre areas. And then we also have those regional sensor data source where USGS and EPA and other agencies actually also provide measurements. And then we also have the radar and the satellite remote sensing. So on top of that, on the right side, we have multiple models we want to actually use the data and the region that we want to study. And the scale of those models increasing from the bottom to the top on the right side. Palms model is basically a plot scale model, and then you have through and descent, which is at the scale of watershed, and then you have greenhouse gas offset model and climate change model, CWRF, which are at the scale of regional continental scale. So we have a group of researchers and developers at Illinois try to use and develop the system to study the areas that we are interested in. And the challenge is basically how we can actually produce a holistic approach to treat both the model results and the sensor data and the derived data products together, and then providing a visualization as well as other service. And ultimately, you can actually change both the behavior of the sensor as well as the management practice in the agriculture field that this site is supposed to be. So I want to give you a more detailed example regarding a particular model, just one model that maybe highlight the diverse needs of those variables and input and processes. So Palm's model is basically a precision agriculture landscape modeling system. So it basically models soil canopy and those processes, and as well as other transport process in a relatively small region. And even with that kind of relatively small scale models, you will have quite diverse inputs need. And you need soil moisture and property measurements. You need topography, and you need hourly weather, and also other remote sensing data from NASA. And you could have very diverse outputs. Of course, it's grid-based, but then you could produce various interesting outputs. So that's basically just give you a background of some of the interesting complex environment systems that we are working on. But the main challenges that we have to solve before even we can tackle any ultimately solve those complex environment system problem, we actually have two challenges. One is the lower the barrier to resolve data, information, knowledge resolution gap problem. Basically, that refers to not only the spatial temporal semantic difference between raw sensor data stream and user design resolution for modeling or decisions support needs, but also enable user to generate those kind of virtual sensors. And I will give some more detailed background information about that. And then second challenge is to promote community participation and sharing by providing provenance-aware virtual sensors. And this is because people want to verify and understand how you actually produce them and across many layers and scales once you actually enter into model-based transformation. So actually, the concept of virtual sensor, we actually proposed a couple years ago. Basically, this is as a background information, how we actually defined originally. It's a product of thematic spatial or temporal transformation and aggregation of one or multiple raw sensor measurements. And then results are then republished as new live persistent virtual sensor streams with provenance information in near real time. So the characteristics of virtual sensors is more on the raw sensor data side, where you can do error correction, QA/QC filtering, spatial temporal coordinate transformation, spatial temporal measurements, aggregation, and then you produce the new virtual sensors. And it could be point, polygon, or grid-based, and it should be ready for downstream physics-based model needs, and it can be created entirely in the cyber world, which can be implemented as parametric workflows. So you expose some parameters, allow user to define how those virtual sensor products should be. So those are the background and the previous definition we have. And once we progress on the study, and we realize that an extended virtual sensor system is a better conceptual framework to encompass all the needs we actually need to meet. So here is basically our idea on how we actually can unify all the knowledge, information, data streams that we need, and then republish them as georeferenced streams. And then across all those layers, we can have upscale or downscale model-based transformation, and we can have provenance mashup across layers. And we feel like this is a good unifying concept framework for describing both raw sensor data as well as derived products. And it's not just about treating or transforming or doing QA/QC with the raw sensor data, but also can be any information and knowledge products. And we enable pervasive application of provenance-aware virtual sensors across scales. And so they are no longer just doing transformation on raw sensor data, but also we can now describe all those modeling approach as part of the extended virtual sensor transformation workflow. And at the same time, we will be able to keep and publish provenance information together with the virtual sensor streams. And finally, I think the interoperability issue is also critical when you actually need to eventually work with all those layers of derived virtual sensor streams. And by using a virtual sensor concept and unifying the representation of those, we could easily use those standards that are already out there, and we can keep them compatible, such as the Open Geospatial Sensor Web Enablement standards, and use like a sensor observation service or SensorML to describe those. So this is just our existing prototype architecture, but I give you an idea how we actually can approach this. So at the bottom is basically some remote sensing stores, and then in the middle is basically what we have been investing and developing middleware as well as service, so that you could manage and provide content and provenance information through a tuple middleware where we developed at NSSA, and workflow service which actually integrated the model, and GeoStream data service where you allow georeferenced streaming data to be fetched, indexed, and queried, and providing virtual sensor abstraction and management service, so you can actually provide in high-level deployable virtual sensor at the user's hand, so they don't have to actually deal with the lower-level details of how they work. And then, of course, you could provide any kind of web user interface that allow people to interact. And so this was actually an old demo that we did in ACM-GIS 2008, providing an example of virtual sensor data stream where you can actually allow people to point and click, say I want to create a virtual rainfall sensor, a point-based one, and then I just click here and I say I want to create one, and then you deploy there, and then 20 minutes later you can actually get time series data for rainfall value in that particular location. And what it happens behind the scenes is basically this high-level construct of virtual rainfall sensor actually invoke a workflow in the back end, retrieving National Weather Service radar data to interpret it into the particular location that you need. But this virtual rain gauge is basically a ready to be deployed virtual sensor artifact that you are using. Another example, which was demonstrated in ACM-GIS 2009, was an example of virtual sensor information streams where you can actually visualize in real time Polygon-based virtual rainfall information in, for example, arbitrary polygon areas user provided. And the example we provided here is basically user-provided sewer-shed polygon areas, multiple. I mean, there are more than 200 polygons within this Chicago areas, where you submit this KML file, which contains all the polygons you want to generate those virtual sensor streams, and then behind the scene, it triggers another workflow to retrieve the next read information, and then doing polygon-based average calculation on transforming reflectivity, which is next-read actually measures to rainfall information in a particular polygon. And again, this become a utility and service where you actually allow people to provide a user-defined modeling region of polygons. And you can then actually publish the virtual sensor itself as OGC sensor web enablement compliant SensorML format, where you can you have multiple ways actually doing this, but this basically shows a SensorML format where you provide some simple derivation history as well as the method that actually you derived it. But in the later part of the presentation, I will actually show you that we can actually go further beyond this kind of XML information, but actually provide a graph-based provenance mashup across all layers that are involved with the creation of virtual sensor. So you can actually examine frame by frame how this derived data product or information product history or what was created. So just give you an example that how all those pieces come together. So this is basically shows you like the spatial temporal rainfall distribution that we saw in previous slide. So what's happening behind the scene, which is basically the bottom half, is basically there's a Next-RED service providing the data feeds, and then we have our internal, we have an external data fetcher which actually fetches data from Next-RED, and that triggers a workflow which has multiple steps, but in that workflow which embeds the model that you need to do the transformation. And then the result was published as a KML stream in the repository. And in the front end, you basically can animate and show the movies of, for example, last hours of the rainfall distribution in those polygon areas by reading the KML streams from the repository. And this just gives you an example of how all those processes are involved in creating this. And later on, I can show you the actual provenance across all this user interface visualization layer, as well as the workflow and the external data fetcher, which is basically sort of like a cron job or a daemon external program, and how those provenance information can be tied and meshed up together. So I don't want to go into too much detail of a theoretical discussion of any provenance or open provenance model, but to give you an idea of how we did it, I have to give a brief introduction of that. So basically, provenance is a description of how the digital object was derived and the causal relationships between those artifacts and processes. So this basically is a OPM simplified representative OPM graph where you have artifacts and processes, and the relationship between them could be an artifact used is used by a process, and the process was generated by an artifact, etc. Or the process was triggered by a process, another process. So you can find all those vocabulary and standard specification online. And we actually take advantage of this open provenance model and use that as our basis to do the provenance mashup. And previously, provenance information was usually tied to specific workflow frameworks, which creates interoperability challenges among different workflow systems. In the virtual sensor system that I just described, we have computation and process that are not just related to workflows. So this includes, just like I mentioned, the user interaction, standalone Java daemon processes, open, and other things. So OPM allow us to do this mashup. And so in the end, we were able to actually publish the real-time provenance-aware virtual sensor on the web, where you can actually click frame by frame to see like what kind of provenance mashup graph we can actually see by, for example, the user interaction part. So when user actually uploaded a Polygon-based virtual sensor, how those actually changed the stream as well as the frame that was affected by that. So basically, we add another component in the stream for the backend workflow to process that. And again, it's a little bit harder to read, but basically this is a provenance mashup across from the sensor observation data packet. We are starting from here. This one triggered an external fetcher, which this in turn triggered a complex workflow. This is a multi-step workflow, and then finally produce an actual data frame in that derived virtual sensor streams. So this is not just one pieces of a provenance, but actually across all layers. And I just give some short description about what we are currently doing. We have a new project funded by Microsoft Research doing digital urban informatics. And what we are trying to do is bring all those real-time observation as well as real-time forecast model to do real-time flooding control or other type of control strategy optimization. And in the meantime, we also would like to add user or participatory sensing component, and such as like a Twitter information. So traditionally, actually, those citizen sensing data were not integrated or interoperated with other sensor data. And the use case that I mentioned right now is part of the South Florida Water District, Water Management District case, where they have a separate citizen line, citizen calling line, but they never use that because citizens basically call and then say a few events in their neighborhood, such as broken sewer, house flooding, etc. What we really want is to put this kind of citizen sensor data, which is in terms of scale and diversity is very different from the traditional engineer survey data, into a georeferenced stream and then published as KML event virtual sensor stream, so you can actually integrate with other type of virtual sensor. So I want to summarize what I just present as a final slide. So scaling the science is about both the increase of the size as well as the expansion of the scope. So the environment informatics is basically a perfect example of that. And an extended virtual sensor system basically provides a unifying conceptual framework for describing provenance-aware virtual sensor across layers and scales, where you no longer just say this is just the sensor data, but this is the model-based derivation. And the example basically is just the first step. We want to show that this is possible. And our current ongoing work including integrating citizen sensing and multiple model-based virtual sensor for decision support. And this will ultimately reach the goal of, from user perspective, that you can visualize and integrate all this heterogeneous sensor-derived data as well as derived knowledge, where the knowledge could be those actionable control strategy from the perspective of the example that I gave. You allow people to control closed gates at a certain time period at a certain location. Okay, thank you.
Couple quick questions. Jinjin from Syracuse University. I'm not a scientist, but from information science, I'm curious about when a data stream, raw data stream, becomes information stream or knowledge stream. I think those concepts are interesting.
Yeah, so we actually come up this idea by brainstorm with quite a few people within computer science and cyber infrastructure area. So the definition of data, information, and knowledge itself is pretty flexible. But the example I gave here is basically saying, if you have actionable knowledge, like the control strategy that people can actually use to do something, I would call it knowledge. You actually can act upon it. You basically, you are given some instructions of to do something. And then the information is more like the higher level situation awareness, visualization kind of, because we talk about the real-time Polygon-based Rainfall distribution visualization, where you don't get it from the data products that you get from like a National Weather Service. So those kind of information stream is, it is more like a situation awareness, but you still cannot do something about it. So yeah, and then data stream is more like just the original QA/QC and error correction kind of type of derived simple derivation. Maybe not necessarily simple. I mean, from QA/QC aspect, but it's still much lower level processing. Okay.
Thank you.
Okay. Thank you.
We didn't see you, so I was wondering. So our next speaker is Rafael Santos.
Santos.
From Brazilian Research Institute Space Institute.
Hello. I will be brief, so I have some time to ask the questions to the other presenter. My name is Rafael Santos. I'm going to present a statement paper on the status of a project that we have been executing in Brazil at the National Institute for Space Research. I'm presenting, but I'm only the computer science guy, the tech guy for the project. We have Maria do Carmo and Celso that are other investigators on the project. Sorry. The problem that we have is that we have to measure, we want to understand better how the atmosphere and the biosphere on a forest environment work together, which kind of influence one have in the other, and what happens during the day with the carbon budget, the regional carbon budget, with the evaporation, with the heat transfer inside of a forest environment. It's a little bit hard to measure that on a forest environment, first because forests are by definition not close to the research centers. So we have to go to the forests and we have to measure there what's happening. Okay, so it's working. It's a little bit hard to see, but there's a lot of stuff going on in the forest. This part of the presentation was provided by Celso, who is an Earth science environment researcher. So he can talk hours about what's going on. For me, it's a bunch of things that float and get all down on the floor. But basically, that's a lot of interaction going with the atmosphere in the canopy of the forest. Honestly, we tried several times to understand that, but that's why I choose computer science, and that's why he chose Earth science. I've tried also to explain how a server works to him, but it's a sort of a personal revenge. He doesn't get a clue about that. But how are you going to do that? We plan to put a sensor of networks with a very high temporal and spatial resolution inside of the canopy of the forest to measure what's going on in the temperature, with the humidity, and we can measure also the carbon concentration on the atmosphere. So we have the sensors. We already have sensors. We already have a pilot to measure temperature and humidity. We are trying to get some kind of reliable carbon measures for this environment. This sensor must be inexpensive. They must be really cheap, so we can put a lot of them under the forest, under the canopy of the forest. And we are going to put them really, literally hanging on the forest, so we can measure several different levels what's going on with the exchange of temperature and humidity, and hopefully for the carbon. And we have some sensors that are not related with the mesh, with the network of sensors, but some local sensors for rainfall and other ancillary measures. So we have this project that's funded by Microsoft and FAPESP. It's based on a project. Actually, it's based on another 2 projects. One is Life Under Your Feet that people are doing on Johns Hopkins University, where they already have these sensors measuring some, I think they're measuring most soil measures. And we have a project that's also funded by FAPESP with some people from São Paulo University, where they already have a deployment on a site that's measuring exactly what we want to do, but in the tropical forest. And we want to put that. First problem that we have to have more reliable sensors, not reliable in the sense of reliable measure, but some more durable sensors, some sensors that we can just put on the forest and forget about them for at least for some days. What else? And we are going to play a lot with the development of database tools for first ingestion of this data on a database, then for visualization, report, and data mining of this information, so we can get the data and put for the earth scientists to play with that and try to understand what's going on in the forest. That's an interdisciplinary team. That's Maria do Carmo and a postdoc student are working on the sensors. They are doing a lot of research on which kind of sensor, probably ceramic sensors, are going to withstand the conditions on the tropical rainforest. It seems that commercial sensors are good for a normal environment, but inside of the forest, it's very hot, it's very humid, and there's a lot of monkeys, so they have to have special sensors. And I'm working with the database. Actually, I and a colleague at INPE and some 2 students are working on database visualization and data mining for Celso, who is the PI of the project, which is going to make the real analysis on the data and drive the whole effort. So what we did so far is we have some prototypes of the sensors, but don't have them integrated with the modes, with the sensor collecting units. We have the sensor that are being calibrated. They are trying to develop these sensors. Since they are prototypes, they are a little bit expensive right now to be put on production. So they are working on with a Brazilian company to try to make them cheap enough to put several of them in several different data collector units. We already have, they are studying these data collection units, the modes they call, and we already have some database development done because we borrowed 2 sets of data that are very related to this program. So it's just a screenshot of a tool. It's something that we are just playing with because we noticed that seeing the data is not useful at all at this moment. It's not useful at all for the earth science guys. They want to see the data with something more. They want to see a very basic analysis, at least, instead of just seeing the raw data. We are playing with that. That's a tool that's was developed from the São Paulo University team that shows the vertical temperature variation during the day, and they have sensors in different heights from the ground. So they have this kind of a profile of temperature. We want to play with this data. We already have this data. We don't have the data for all the deployment, but we want to play this data to try to locate blankets of high variation on temperature. That's what one of the students is doing right now. I don't have any result to show, but just sort of this, but in 2 dimensions. And I'd like to talk a little bit about the deployment sites. There's the first pilot deployment that was from the São Paulo University team that's actually close to São Paulo. That's a place. That's a tropical forest. It's not as bad as it looks because it's very close to cities. It's around 2 hours and a half driving from São Paulo. It's 1 hour drive from INPE, where we sited. But anyway, they have some, okay, this is fake. That's the only tower they have is this one. The others are fakes. But they have some towers there, and they hanged some Kevlar cables. And from the Kevlar cables, they do something it looks like a poor man's Christmas tree, with a lot of sensors hanging out from these masts, and they have also some sensors that are on the ground. This is basically the map with the towers, the cables, and the number of the sensors. You can see here, each one of these number in the black box, one of the sensors they have for temperature and humidity. They also have a line that's just over the ground to get these measures. So that was a pilot experiment done with Johns Hopkins University team. We have some data for that we are playing with that until we get the chance to put this stuff in here, in the Amazon. So these people are crazy enough to go to a place that's Manaus City should be around there, and they are crazy enough to put it, I think it's a 60-mile from the city in a drive that you just have to go to in the middle of the forest. They are going to drive there. They already have 1 tower. They are going to hang cables there and try to measure the same stuff for the rainforest. That's the rainforest. It's very famous because there's nothing there but trees, monkeys, and eating things that eat people. So mosquitoes this size. You know? Okay, I'm joking. The mosquitoes. I'm joking, but anyway, it's a nice idea because we are going to put sensors that they need to be reliable. They need to be resilient enough to work for more than half an hour at least on this kind of environment. And also, I forgot to tell, it rains a lot there, and it's a lot. Okay, one of the problems that we are going to face is that we have to model what the sensors are measuring. We have to going to take in consideration the digital model, the terrain model, because we expect the height of the terrain, also the height of the sensors close related to the ground level, to have some variation. So we are going to use this information that they already have on the site near Manaus. This is the site that's it's very interesting actually because it was early in the morning. They have fog. It's something that around midday they will have 38 degrees temperature inside this canopy. But in the morning they have fog, so they have a lot of variation. As somebody told me, they have a lot of variation in the temperature and the carbon concentration in the morning, in the valleys, in the small valleys that you can see around here on this image. So we don't have it yet. We don't have the sensors. We don't rely on we don't have the sensors to make the deployment on Amazon. But we already have the site. We have a tower there. We're putting another tower. We are creating at INPE sensors, ceramic sensors that are good enough to handle over those trees. And we are just going to try to collect data. I think we are going to have some data later next year. So far, we only have data for 2 experiments we borrowed. One from the São Paulo for São Paulo University, and another one that's a historical collection of data at INPE. We have way much data that we sometimes don't even know what to do with. So I asked a friend for data from sensors, for the same kind of sensors, temperature and humidity. But we have old sensors that are not in a local network. They are very distributed in miles from each other. And he said, okay, how many millions of rows of data do you want? And he gave me 30 millions. And I'm starting to think how we are going to play with that. So we are going to, the computer science development side of the project, we are playing with this data. So we have everything ready when we do the real deployment that's going to be next year. Also, we are thinking about to let people play with the data. I'm not sure if it's a good idea, but we have a lot of environmental data at INPE that's, it's not the central repository, but we have a lot of that. And it's just locked inside of big computers, and people can play with a little bit just browsing on the web on some servers. But we are thinking about making a sort of okay, let's contribute. Go outside and see it's raining. Let us know it's raining, and we are going to collect this data and try to integrate that. But we are still thinking about on how to do that. And that was very quick. So you can ask me a lot of questions, or we can go to a bar.
First of all, thank you.
Questions?
How do the sensors communicate? Are they or how do they
Wireless.
You
Wireless.
want us to repeat the question, right? Yeah. So how do the sensors communicate with each other?
From what I know, they are going to communicate via wireless. They have modes that are connected wirelessly, and each mode have 4 sensors, if I'm not wrong. Then each one are going to connect wirelessly, and we have a grad student that's going on the forest with a laptop and try to cover for the monkeys and try to collect the data close to that. It's more or less what Johns Hopkins people did with the Life Under a Feet program. That's one of the problems they are going to face because you can't get close to a moat. You can't get close to one of those moats. They are going to be hanging on the trees 20 meters from the ground. But we have a very resourceful student that may be able to climb some ropes or something. Actually, we didn't really check. That's one of the problems on the last phase of the project, that we are going to have to check the ability, the distance that we can connect with these moats. But we are quite sure that we are going to get. It's something that you can just walk close to them, collect the data every day, and bring back and send via internet. This place is in the middle of the Amazon, but they have a small hut on there that they have internet connection, light. It's just that it's a small place.
Hi, yeah. Just wanted to comment that at Southampton we have a project called GlaxWeb where they're dropping sensors underneath a glacier. So they have a self-organizing network that flows with the glacier, and they've built sensors that work under a kilometer of ice that talk over radio. So I'll put you in touch with them maybe, because they've been doing this for the last 5 years. And
one of the things that we plan to recover the modes later and try to use them again. So it's something that I'm not sure it's the same idea, but
I'm sure there's a lot of shared experience. Yes.
So when you say that you want people come to play your data, what kind of expectation you have from that? Sounds like you're going to have to put some effort to enable that. Then what are you planning on getting out of that?
We are not planning to use this data because it's very specific data. We don't have people that they just can go to the forest and measure humidity. But we have a lot of meteorological, historical data. And one of the ideas that we had there is that related with outreach and education. For example, we have a lot of schools that teach geography, and one of the problems that they teach, okay, let's say, what's happened with El Nino? And when you have to teach the kids, why not make a small tool that the teacher can get the real data, that we have the historical data for this city, and play with that and say, okay, this year we had something different. Or, for example, it's very cheap for a school to get a thermometer, simple thermometer or a hygrometer, and put on the outside and ask the kids, okay, let's go to INPE, collect the data, all the data that you had from your city on this period, and compare that with what's going on. We don't have a very clear idea on that now, but since we have the data, why not put the data so schools can use them for any kind of project?
Right.
So it's it's not exactly like people contributing data, but using the data to outreach and public education.
So then that would be supplying the data like real time. Whenever you have an update, they have.
No, it's more historical. We already have systems at INPE that give the real time data, and we have a lot of people that work on climate research, and they have.
Yeah. Okay.
But it's going to be historical data.
Any more questions? Okay, that concludes this session on sensors.